So, hello, Physics 72 LE2 takers. Welcome to another organic chemistry video. And for our resource today, we will be using second LE of 2016-2017. So, big disclaimer. This is almost 10 years ago, but this was the only one that this is the most recent one that I can find in the iClub Rainbox. So yeah, there's that. Um, Obviously, the questions here are very similar to what we have, but there are obviously some things that are not included. For example, in these set of questions, there's no LRC, um, mostly to do with inductors. There's none of them here. But so the best way to review is the problem set that we have right now, the current problem set that we have that is due on April 11th day. So if you haven't done it, please do it. It's probably the best. It's the best resource to have. Also, but there's also another resource that we have. It is this one. Wait, sorry, this one. This can be founded in the Rainbox. It is a just a quick summary of all of the lessons that we have. This explains so much, and this will be the perfect reviewer for you. But this has everything that we need. This has all of the solenoids. These are all of the everything actually. It basically just has everything we need. This is the best one so far. Whoever took all of those notes, thank you very much. Yep, this can be found in the Rainbox. All right, and let's just get started. So, disclaimer again, 10 years ago. All right. So for number one, okay. So for number one, what is the relationship between the magnetic fields, magnitude point X and Y? So this it's magnets north. You can just see from the arrow lines, but north produces the magnetic field line, south absorbs it over here. So what is the magnetic field at X and Y? So over here it's B X is greater than BY because the magnetic field is inversely proportional to spacing of the mag. So the more spacing there is, so like over here would be less than Y, which is then which Y is less than X. So it's like electric field lines, but with magnets. Okay, for number two, if a charged magnetic Q is moving instantaneously upwards at point X, what is the direction of the magnetic force? So, first things first that you should always remember, it says negative Q. If it's a negative charge, we're not using the right hand rule, but we're using the left hand rule. It's the same thing as the right hand rule, but you just use your left hand. So first, moving instantaneously upwards, and we know it's at point X, which is using this one. So the magnetic field line is towards the right. So the magnetic field line is always your middle finger. So point your middle finger towards the right. And we know that it's moving upwards. So move your pointer finger towards up. So right now your thumb is pointing towards you, and that's why it is um, it's pointing away from the page. Okay, for number three, a cone with a base area 1.77 and a height 2.4 is immersed in a uniform magnetic field. The magnetic flux through surface X is plus 0.4. If the angle between dash line and magnetic field line is 30 degrees, what is the magnitude of the magnetic field? So first things first, X is equal to Y because there's no since the magnetic flux, if you add them together, is equal to 0. So that means X and Y are the same, and we know that Y is to get the magnetic flux, it's B times A, B dot A. So we have this. Our area is we can find the area over here. It's just 1.77, 1.77, which is 1.77. But the area vector is over here, right? And since that's the area vector, that means the angle for between the magnetic field is 150 degrees. So that's the angle that we have to be using over here. So it's just plug and play. Negative 0.4 is equal to B A cosine 150, and for that we have this 0.261. So next, for number four, Consider a magnetic force vector on four charges as shown. The charges are all moving upwards in a uniform magnetic field. What is the direction into the page? Which charge is the most positive? So over here, so we know that the field is into the page, and we know that these things are moving upwards. So we have to use the right hand rule. So into the page is our middle finger. So into the page is our middle finger, and up is our index finger. So boom boom. So our thumb will be over here to the left, and we see these. B has a bigger line, so that means B is the most positive. B is most positive. All right. Next, for number five, an electron is initially at the origin at velocity v naught I. If there's an uniform uniform magnetic field at positive k, what is the direction of the electron? So if we do a cross product for force over here, we know I cross k is negative j, but since there's a negative e, negative j becomes positive e, positive j. So right there, we can already find that A is already our answer because it's the only one with a positive positive like center, because over here it's positive j. But to to confirm it even more, we can find the rotation of it. So if we use the left hand rule, because it's an electron, so we use the left hand rule. Um, it says that velocity is positive I and magnetic field is K. So middle finger is pointed towards you, and then your pointer finger is pointed towards the right. So the force is upwards. So we know that it curves upwards, and that's why it's a counterclockwise rotation. So curves over here and becomes counterclockwise. All right. For number six, consider proton with a velocity v naught k entering a uniform magnetic field v naught I plus j. What is the cyclotron radius? So we know that from the list of equations that the cyclotron radius is r is equal to mv over qb. So plugging that in, we get mv mv over e b. But we know that our b is I hat j hat, and I hat j hat uh, if you just make it into a magnitude, it becomes square root of 2. So it's mv all over eb square root of 2 on the underside, which is equal to c. Consider a quarter circle wire with radius r and current I directed as shown. If there's a uniform magnetic field B equals B naught negative k, what is the y component of the net magnetic force on the wire? So this equation can be found from this one, F equals ILB. Where is it? There. F equals ILB. So DF equals IDLB. And with that, using that, we can plug this one in, which becomes IRD theta x b negative k. So b is negative k over here, and then yep, and so we cross this. We just cross product this IRB d theta negative r. The reason why it's negative r is because it's negative k and theta. So negative r, that means it's just the direct this one. This is the direction of it towards the center. So getting the dfy is equal to df sine theta negative j negative IRB sine theta d theta. And we just have to reverse the derivative, so we integrate it. So negative IRB theta 0 pi over 2 sine theta d theta j is just equal to negative IRB j. So over here, negative IRB j. So to just simplify this, or to give you the idea of what to do during this, is just get the first derivative of the force. So I dlb, I and b should be given, so it's I bb, and then dl will be r d theta, because it's derivative. It's because length the length of a circle is by 2 pi r, and we derive this becomes just r. So even if it's a quarter circle, even say like a third of a circle, it's just always just gonna be r. That's why it is r d theta theta. For number eight, A loop carries a current I as shown and is immersed in a uniform magnetic field B equals B naught J. What is the direction of the torque of the loop? So first, we use the right-hand screw rule, and we know that since the current is moving clockwise, the current is the is into the page, the U, the mu I meant. So we know it's into the page, which is negative K. So that's why there's negative U K. And we also know that the magnetic field is B naught J, positive J. So if we cross this, KJ, I, J, K, J, K, since it's K cross J, it is negative, it becomes negative I, but since there's already negative, it becomes positive. Just as a reminder on how cross products work, just in case you don't know, what's it so big? IJK, IJK. So if it's I cross J, it becomes K. If it's J cross K, it becomes I. If it's K cross I, it becomes positive J. And if any of them are flipped around, it becomes negative. So if it's J cross I, it becomes negative K. If it's K cross J, it becomes negative I, and so on. So it's just IJ, JK, KI. And if it's not following that order, and then it is negative. So for number 9, consider current carrying loop placed inside which of following is true about the loop. So first of all, we know that there is no torque at all because with this I, this means the magnetic field is here. So if you cross product these two things, it's going to cancel out to zero. So there's no torque. And since there's no torque, it's not going to rotate because there's no torque. So now we have to find if it's unstable equilibrium or has minimum potential energy. They're like opposites of each other. If it's stable equilibrium, then it has minimum potential energy. So it's here and here. And since these two things are anti-parallel from each other, basically they're not doing the same thing, then it's an unstable equilibrium. Okay, next. Consider 2 bar magnets and 4 compasses whose directions are in relation from left to right. What are the indicated polarities? So basically the way this works is we just have to remember the magnetic field lines. So imagine a line over here, there's a line. And since the compass is pointing there, the field line should look like this. So that means this is south, this is north. And then just do the magnetic field line over here, north, north, south. So south, north, north, south. It's just compasses follow the magnetic field lines. That's just all you have to remember. For number 11, which of the 4 wires have the same magnetic field direction as that as wire 4? So we can see it over here. It's just using the right hand screw rule. So 4 is pointing into the page, into page, into page, out of page. So it's here, 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 here. But it's asking for at point P. So at point P, you can see it here that 1 and 4 are going the same direction at point P, but the other two are going on the completely other side. So for number 12, it asks what is the net magnetic field at point P. So we know that these two things cancel out. 4 and 1, the 2 and 3 cancel out already because it's going and they cancel each other out. So we have now this. We have we have 2 lines going there. So the equation that we use for this will be just from the list of formulas will be this. B is equal to U naught I over 2 pi r. So with that, here, sorry, there we go. B is equal to U naught over 2 U naught I over 2 pi r. So 2 pi r, and we know that from this r will just become square root of 2, but since there's 2 of them, it just puts 2 over here, so cancel out, right? Yeah, square root 2 over 2, got there, 2 pi r, 2 pi r, 2 pi r, there we go, so it becomes u naught I over pi r square root of 2. Oh, yeah, and then first we rationalize this, so it becomes 2 square root of 2 over here. That's this rationalized. But a tricky thing about this, from after this part, a tricky thing after this is that we have to look at the signs because these is I plus j. So that means we need to we need to get we have to divide by cosine 45, cosine 45, sine 45, cosine 45, which is equal to square root of 2 over 2. So if we divide by cos 45, cancel this, cancel this, cancel this, so it becomes u naught I by r. It's just this one. It's just a. That's just a there. For number 13, consider the top view of circuit compass 1, compass 2, placed directly above as is shown. When the switch is closed, how will the compass needle be deflected? So current goes from positive, negative, so it's like this, right? And with respect to compass 1, since the current is going down, it will be deflected counterclockwise. So to the left over here, so it's counterclockwise. And if you follow it, go up, it goes up compass 2, so it's goes clockwise. So it's C1, C2. Just quick. For the next two items, consider two conductors whose cross-section, shaded region, are shown. Both conductors have the same uniform current I, but in opposite directions. Inner conductors is into the page, out of the page. So it's out of the page, into the page. So what is the direction of the magnetic field along the circular loop with radius r? So we know that since the circular loop is like only a little bit into the second conductor, that this one, the A is super strong. So we will take priority of A, which pointed into the page, right hand rule, clockwise. So for number 15, what is the what is the magnitude of the magnetic field along this circular loop? So we know it's not zero because there is a magnetic field. And we also know that it's not plus because they're moving in opposite direction. So it's one of these two, right? So the answer is C because this is just the um, equation of Ampere's law. It's r squared minus b squared over c squared minus b squared. So it's just that radius minus b over c minus b. Yeah, that's just the equation. So it's not zero, it's not plus, and we can just find out from one of these two. So for number 16, a wire bent at a right angle carries 14 amperes current as shown. Consider two 7mm segments of the wire, each 9 cm from the bend. What is the net magnetic field due to these two segments? So we will be using this equation over here. Why is my pen so big? So we'll be using this equation, right? And then so u naught I, this is just a constant. This is just a constant. You can count and r is 0.009 over square root of 2 because that's 0.09 square root of 2. That's just the distance over here. DL is 7 millimeters. So, and then R is 45, sine 45, because it's 90 degrees, sine 45. So, plugging it in, it's just this 2, 1 times 10 7, 14, 0.7, sine 45 over 0.92, which is equal to 3.42 times 10 to the 6. And to find out if it's into the page or out of the page, remember there's the current over here. So current is over there, so it's going clockwise. It's moving clockwise, so that means it's into the page. All right. So for number 17, consider a negative 4.8 microcoulomb charge located at the origin and moving at constant velocity. At this instant, what is the magnetic field vector at 0.5, 0.50? So we'll be using this equation, which is given in the list of equations. And u naught for pi is a constant is given. So right now we just want to find what is r hat and r squared. So r hat is equal to square root of 2 over 2, square root of 2 over 2, and same with r squared. And same with r actually. R is equal to square root of 2 over 2 as well. So using that, using this, v cross r hat will just become vk square root of 2 over 2 VK, and R is also square root 2 over 2. It's just square root of 2 over 2 because it's not a vector. And plugging that all in, we will get the negative 4.62 times 10 to the negative 7. Number 18. A circular coil has 800 turns, radius 2.4 cm. If the magnetic field magnitude the center is 5.8, what's the current of the coil? This is a plug and play equation over here. B is equal to U naught Ni over 2R. And so we just transpose, and I would become equal to 2BXR U naught N, which is equal to C, 2.77 times 10 negative 2. Next, for number 19, two straight parallel wires carry currents in opposite directions. One wire has a current of 5 amperes, while the other has 2 amperes. If the force per unit length on each wire is 1 times 9 for how far the two wires. This is also given. The equation of this is this one. Force per unit length is U naught over 2 pi I1 I2 over R. So it is, what is it? U naught 2 pi. U naught 2 pi over here. So let's see on this one. Force per unit, U naught I1 I2 over 2 pi R. Rearranging it, R is equal to 0.2 mm. Okay, for number 3. So which of the for number 20, which of the following gives the correct directions of the currents I1, I3 through R1, R3? So we can see here there's a magnetic field into the page, so that means the thing is clockwise. Yep, there we go. It's clockwise. Is it clockwise? Yeah, it's clockwise. So that means if you just expand it, it's gonna be like up here and then up here. But we know that the currents always resist change. So since there's that, it's producing a current that's resist change. So it's over down here. So it's down down I1 I3. This is what the yeah. So for number 21, what is the magnitude of the induced EMF? The induced EMF is just equal to E is equal to the magnetic field times the velocity times the length of the rod. So this is 10, this is 0 0.01, 0 0.1, 0.1, that's like 2, correct? 20 cm, 0 0.2, 0 0.2. So if you do that, it becomes this one, B. 2 times 10 to the negative 1 B. Next, consider two conducting loops as shown below. If the current in the upper loop is increasing with time, what are the directions of the induced current on the lower loop? Um, so since this, if you're okay, so if you're looking at this from the top, this is moving at a counterclockwise direction. That's why this is either it's clockwise 100%. It's clockwise. And then next, um, since since if you use the right hand screw rule and you follow the current with your fingers, the magnetic field is pointed towards up here. So that means it has to be down here. So that's why it's clockwise downwards. Next, consider a setup shown where a solenoid is attached to a galvanometer. A stationary bar magnet is placed on the right side where it can be freely moved. The system is immersed in magnetic field B prime, which of the following would cause a deflection in the galvanometer. So basically in this setup, we did this in the physics 72.1 lab, but if you move the uh, magnet like into the thing, it will change the galvanometer. So same thing, rotating the solenoid about the z-axis. If you rotate it like here, it's like you're moving it away from the entrance of the thing, so it's gonna be deflected. Because this one, it's the entrance here, but then if you rotate it 90 degrees, then it's like it's on the side, which doesn't really affect it that much. Moving the galvanometer doesn't change anything. The presence of stationary bar magnet could be, I don't know, but presence of constant B doesn't matter. And the reason why the presence of stationary bar magnet doesn't do anything is because um, if there's no bar magnet at all, it's still a constant magnetic field, so it doesn't really matter at all. So that's why the rotating is the only one that really changes it, because you change the strength of the magnetic field. Okay, for the next two items, consider a conducting bar with length 0.5 moving at 2 meters per second connected to a 1 ohm resistor as shown. The circuit is immersed in a uniform magnetic field pointed into the page. The bar and connecting wires have negative resistance. So for number 24, if the induced current through the resistor is 2 amperes, what is the magnitude of the uniform magnetic field? So we'll be using two equations. E equals IR, so IR, and E is equal to V, VBL, VBL cosine 60, cosine 60. So cosine 60 is just this one. It's just 90 minus 30. You get 60, and then um yeah, it's just yeah, it's just 90 minus 30, so 60 cosine 60 VBL plus it's VBDL. And then just plugging in all of the equation numbers, we'll have B equals to 4T. So B is equal to 4T. Next for number 25, what are the directions of the induced magnetic field of the circuit B induced, the magnetic induced, and the induced current in the circuit I induced? So since this is part of it for next item, yeah, okay. So B induced is at the page. Yeah, counterclockwise. Into the page, clockwise, counterclockwise. Okay, so for number 25, what are the directions of the induced magnetic field in the circuit B induced and the induced current in the circuit I induced? So we know that induced is just opposite of the change. So since it's into the page and clockwise, it's out of the page counterclockwise. Which of the following statements is or are true? An electrostatic field does not an electrostatic electric field does non-zero work in moving point charge around a closed path. This is wrong because it's always zero. An induced electric field is produced by a time-varying magnetic flux. Yes, because time varying, that means through time the magnetic flux changes, and if the magnetic flux changes, there's an induced electric field. And an induced electric field has a corresponding potential function, not necessarily. It doesn't always have a corresponding potential function because it's based on just the change, not on time. So, so for number 28, consider an underdamped LRC circuit with inductance L, capacitance C, and R, resistance R. What's the value of R that will result in an angular frequency as 90% of that when R equals 0? So first we have to know that W is equal to square root of 1 over LC. And for damped oscillations, we know that this is W naught, sorry. The angular frequency of a damped oscillation is equal to the square root of W naught squared minus R over 2L squared. This is not given in the list of equations, so it's good to take note of this. But then we know since it's looking for 90%, this is 0.9 W naught, and we can square both sides. So it's if we just I'll just do a quick things. It's negative W naught squared um, minus plus 0.81 W naught squared minus R over 2L squared, right? With this, just combining everything is 0.19 W naught squared is equal to R squared over 4L squared. And then we can substitute the W naught for 1 over square root of LC. So it becomes okay, sorry. We can move this up here, but sorry. All right. Yeah, we can move this up here. So it becomes 0.76 um, L squared W naught squared is equal to R squared. And then W naught is equal to 1 over square root of LC. So I'll just combine everything already. It becomes 0.76 L over C equals R squared. So R is equal to square root of 0.76 L over C equal to 19 over 25 L C squared. There's an A. Okay, almost. Okay, so for number 29, an LRC circuit has L equals 0.25 Henry, 1000 resistance, and 1 times 10^6 charge. So which of the following best describes oscillation? So we use this equation. R squared equals 4L over C. And when we do that, we will be getting um, 10,000, 10,000. So it's 10,000, 10,000. So both they're equal to each other. So that means it's critically damped. But if R squared is less than 4L over C, it's underdamped. And if it's overdamped, it's greater than. So this is a good thing to remember. Undamped is like if it's zero. But if it's equal to, it's critically damped. Underdamped is less than. Overdamped is greater than. So that's what to just know. R squared equals 4L over C. For number 30, an LC circuit consists of 1 MF capacitor and 2 mH inductor. The charge of the capacitor is 2 MC. What when the circuit current is 4 amperes, how much charge is in the capacitor when the circuit becomes 2 amperes? So it's using this equation, and that equation is given in the list of equations over here. It is given in the list of equations over here. So we will just be um, combining. We'll just be plug and playing. So Q1 to MC, C1 MF to MH for a Q2. We don't know. We want to find what Q2 is. MF to MH 2 amperes, 5.3 MC. Um, an LC circuit consists of 0.05 farad capacitor and 0.01 Henry inductor. How much time is needed? Current oscillation to complete one cycle. So over here, W equals 1 over LC, Henry farad for 4.7 rads. And rad per second is not, most of the time you have to find it in seconds. So it's period is equal to 2 pi over W. So it's 2 pi over 44.7, 0.14 seconds. Solenoid 1 induces an EMF 50 volts on solenoid 2 by mutual induction. It was done by a uniform change in current in solenoid 1 from 15 amperes to 22 within 3 seconds. What is their mutual inductance? So mutual inductance you can see over here is E2 is equal to MDI. Uh, um, yeah, it's yeah, actually it's over here. Sorry, we know that mutual inductance is here, there. E equals negative M di over dt. So we know that their inductance is where is it? There. We know that their inductance is no, we're looking for inductance. Sorry, so it's negative E over di dt. So we just plug and play. Negative 53 times 96, 22 minus 15. Di, just a reminder, di dt, you can find them on your own. It's just the difference between the initial and final one. Final minus initial. And so it's 2.4 times 10 to the 15 Henry divided by 4. Last one. So for number 33, consider a toroidal solenoid with self-inductance of 3.75. What would be its self-induced EMF? The current is increased to 0, 5, 8, and 5. So the equation that we're going to be using is given in the equation sheet. Is E is equal to L di over dt. And all of this is found di, dt, and L. And the answer when you get all of this is D, negative 37.5. All right. Okay. And that is the um 2017 second long exam. Just as a reminder again, this is old, 8 years already. Like you can like the equations we haven't at all used these equations over here, and these will be part of the long exam. So just a reminder, answer the prob set, that current prob set, because it will definitely help you. You can ask your prof if you need any help. And there is a good reviewer in the iClub Brain Box that discusses everything, even until this one. Yeah, even until phasors, which will definitely be part. So yeah, that's all, and thank you for watching the video.